move on to the next speaker, which is Slade Lankins, which is going to talk about acoustic partitioning in frog assemblages.
Yes, thank you, Diego. I'll just get my hold on. I'll get my screen shared in a moment. My video just got stopped. Oh, here we go. Okay. Okay, I think I'm sharing correctly now, everybody.
Yeah.
Thank you. Yeah, my name's Slade Lankins. I'm a researcher at James Cook University in Australia, and I'm just going to talk today about acoustic niche partitioning in frog assemblages. So acoustic signaling is obviously a very common and important communication method for many different animal groups. And because of how common it is, animals are often in environments and surrounded by lots of different interspecific signals. And all these different signals from different species has the potential to interfere with communication by masking signals of conspecific calls so that it's harder to detect and localize those calls. It can also cause signal confusion so that animals end up displaying inappropriate behaviors or accidental matings. So this interference from signaling in a diverse environment could be detrimental to fitness, and for that reason it's been suggested that animals should partition the acoustic space to reduce these effects. And there are many different ways that animals can partition the acoustic space. They could partition it structurally, so with the structure of their signals. So in this hypothetical example here with 4 different species, they may occur at the same location and signal at the same time as one another. But because their signals differ in the frequency bandwidths that they occupy, this is one way that they can reduce the interference when they signal at the same time as one another. They could also temporally partition the acoustic space. So perhaps in this case, these 4 species actually have quite similar signals structurally and tend to call at the same locations, but they just call at different times from one another so as to avoid interference. And they can partition this temporally at different time scales. So this could be like a seasonal time scale where species 1 calls early in the breeding season and species 2 calls quite late in the breeding season, or it could even be within the same night. For instance, for frogs, perhaps species 1 calls really early in the night before the other species start to call. And they can also partition the acoustic space spatially. So perhaps in this example, species 1 and 2 have quite similar signals and they tend to call at the same time as one another, but they just occur at different locations so that they don't interfere with one another. And so while there's been a number of studies over the years that have looked at acoustic partitioning, and there's been evidence in support of acoustic partitioning for insects and birds and frogs, they've typically examined only a small number of species at a time, or perhaps a small single signaling community. So there's definitely a need to look at how general acoustic partitioning is across different animal groups. And to complicate it further, like Patrick Hart mentioned in his talk earlier, there have been some studies that have put forward alternative hypotheses that signals are actually more clustered for species that occur together rather than actually be partitioning. So for the study that I'm going to talk about today, I wanted to test whether the calls of frog assemblages were less similar acoustically than we might expect by random chance. And I did this with the use of a recently collected data set of frog calling events from around Australia. This was collected between late 2017 and late 2018, so a full 1 year period. And this data set came from a smartphone app that's been developed here in Australia called Frog ID. This has been developed by researchers at the Australian Museum, and using this smartphone app, people that can download it to their phones, and then when they go out in the environment and hear frogs calling, they can make a short recording of 20 to 60 seconds to capture what they hear, and then upload that audio via the app. And then the species that we're signaling in that audio clip get validated by the herpetologists from the Frog ID team. And so this has been going for a couple of years now, and this was the first year of the data set that they collected. And essentially what it has is a lot of calling events from around the country that contain frog species that are calling at the same place and at the same time together. And so I wanted to use this to see whether their signals were more or less similar than we might expect. So in the data set that I looked at, we had a minimum of 4 species calling in each recording and up to 11 species. So there's definitely potential for competition in the acoustic space when you have 11 species calling within a 20 to 60 second period. And so this represented 1,641 different calling events and a total of 86 different frog species, which is a significant proportion of Australia's frog fauna. And so for each of these different species in the dataset, the 86 different species, if I wanted to have a look at how similar their signals were, I measured a number of different parameters of their call. So I measured 3 different frequency parameters. I measured the 5th percentile of their call energy, so essentially the lowest sort of frequency of their calls, the 95th percentile of their call energy, so towards the upper end of their call frequency, as well as their dominant frequency. And I also measured 3 other call parameters that are sort of more temporal call features, so the pulse rate, the number of pulses within a certain duration of their call, the duration of their call that contained 90% of their call energy, as well as the relative position within the call where the peak energy occurred. So whether in this example it occurs late in the call, but for some calls it might occur in the middle or early on. And so using these parameters that I measured for the 86 different species, the goal was to determine for each of those calling events in the data set, those 1,641 calling events, I wanted to determine the acoustic similarity of the signals in those events. And so I went about that in 3 different ways. The first way was to consider all 6 of those calling parameters that I just mentioned. And using a PCA for all of the species on those 6 call features, we were able to measure the distance between any pair of species in the data set that we wanted. So for example, in a calling event, we might have species 33 and species 30. So we can get the distance between those 2 species calls. Perhaps 72 was also signaling at the same time. So we can measure the distance between 33 and 72 and 30 and 72. And maybe 52 was in there as well. So we get the distance between all of the potential pairwise comparisons for the species that are signaling together in a calling event, and take the mean of those values to get a acoustic similarity value for that event. So for those 1,641 calling events, they have different species compositions making them up, and we can get an acoustic similarity measurement for those events. And so that was the first way that I measured acoustic similarity. I also measured them 2 other ways, just focusing on frequency parameters. The first of those was spectral overlap, so looking at the amount of overlap between each species' 90% frequency bandwidth. So that's the difference between their 5th and 95th percentile of call energy that I mentioned earlier. So in an event like this, we're looking at how much does the bandwidth of species 1 overlap with species 2, species 1 with 3, and so on for all of the potential combinations for the species in that event. And then we take the mean of those again to get the acoustic similarity for that calling event. And then the final way was using a frequency parameter again, but this time dominant frequency. So we just measure the distance or the difference between the dominant frequencies of the species that we're calling in that event. And once again, just take the mean of all the pairwise comparisons for that. So this would give us 3 different measures of acoustic similarity for those 1,641 calling events. And these would be our observed values of acoustic similarity, but this doesn't really tell us whether these values are indicative of acoustic partitioning or whether they're just perhaps arising out of random chance, or perhaps they're actually more similar than we might expect. So for each of those observed values, we generated random acoustic similarity values to compare them to. So for each of the observed calling events, I generated 1,000 random calling events of the same size. So if a calling event had 7 species calling, then I would generate 1,000 random calling events that also had 7 species calling. And in all of these random calling events, I could measure the acoustic similarity in the same way as I just mentioned for the observed events. And the species that would go into those 1,000 random calling events were based on the species that occur within 50 kilometers of that observed event. So in this little animation here, each of these dots might represent one of our observed data points in the data set. And the species pool for that observed point would be all the species that occurred within 50 kilometers of that event. And so that would give us something like this. This is an example for spectral overlap, where we have the results of 1,000 random calling events and the amount of spectral overlap in those random events with the species shuffled. And we can compare that to our observed calling event. So in this example, the mean spectral overlap for the observed species in this event was 0.14. And the random calling events was 0.33. So in this instance, our observed calling event, the amount of spectral overlap between the species that called together was less than our random calling events might have predicted. So this would provide evidence of partitioning. Another example, in this case, the observed calling event had a mean spectral overlap value of 0.3, but the random events had a value of 0.25. So this time, the signals for the species that actually called together overlapped more than we might expect based on our random calling events. So this might be some evidence of clustering. And what we can then do is do that for all of those 1,641 events, comparing our observed values to the random values to see whether they are more often than not showing evidence of partitioning, or whether they're simply random. So if they were random, we might expect that just as many calling events showed less acoustic similarity as showed greater acoustic similarity than our random calling events. If there was partitioning going on, then we would expect that most of the calling events would have calls that were less similar than predicted under our random calling events. And if there was clustering going on, then we'd expect that most of the observed calling events would have greater acoustic similarity than our random events. So what do we find?
Sorry, 1 minute.
No worries, thank you. So when I looked at all 6 call characteristics, we found that 57% of the observed calling events had less similar signals than the random calling events. So that's in the direction that we'd expect if there was acoustic partitioning going on. It was similar for spectral overlap. The graph direction is flipped this time because we're talking about the amount of overlap rather than the amount of distance. And 70% of the observed calling events had signals that overlapped less than the random calling events. And for dominant frequency, it was a similar story again, with 59% of the observed calling events having less similar signals than the random events. So there was a greater distance between their dominant frequencies. I'll just quickly go through this. The more species that were in a calling event, the stronger the evidence for partitioning was. So breaking down between our 4 up to 11 species calling in an event, when we got up to say 9, 10 or 11 species calling together, they pretty much always had a greater distance between their calls than we'd expect. For spectral overlap, they overlapped less than our random events once there was many more species in the calling event. And it was the same for dominant frequency. And to wrap up, so we examined the co-signaling events that contained almost half of Australia's frog species and found that the majority of observed calling events had calls that were less structurally similar than random calling events. And the more species that called, the stronger the evidence for acoustic partitioning. So it would seem that partitioning of the acoustic space is common for Australia's frogs. And yeah, thank you.
Thank you so much. It's great. So now a few minutes for questions. Okay, so Renata Sousa-Lima asks, can you detail the measurement of a spectral overlap using the 90% bandwidth of a species calling? Did you use a mean value for all pairwise calls?
Yeah, so I guess I sort of use two there. So so if you're comparing species 1 to species 2, species 2 might overlap species 1 by say like 10% of species 1's call, whereas species 1 might overlap species 2 by like say half of its call bandwidth, because they might have different widths to their call bandwidths. And so a comparison between one species and another would be the mean of those two values. And then for the whole signaling event, I would take the average of every pairwise comparison. I hope that makes sense.
Okay, another question from Roseanne. Thank you for the talk. Have you tried other embeddings besides PCA?
So no, when we've looked at the 6 different call parameters, we've only used the Euclidean distance from a PCA on those 6. We also did it separately on just frequency and temporal parameters, and that's when we found that there was actually no difference between our observed and our random calling events with respect to just temporal call features. So that's why I've sort of focused on the frequency call features today. But yeah, I'd be interested in any other methods to sort of measure those distance between the similarity of calls.
Okay, I have another question for you. I'm wondering how can we interpret the pattern that you see, which is quite interesting. No? You found that there are, most of the cases are, you find niche partitioning, but I guess we can think on different processes explaining those patterns, right? I don't know if you plan to statistically test different mechanisms behind those patterns. Like I'm thinking, when we talk about niche partitioning, we think on competition during calling behavior and masking interference, but there are, as you know, other processes like phylogenetic relationship within the communities and so on. I don't know if you plan to test this thing.
Yeah, there's definitely more that can be done with this data set, and then hopefully with further versions of this data set as we collect more over the years as well. But you're right about the phylogenetic relationship, to have a look at how similar signals are for the closely related species, but also delving more into whether, I guess, the patterns that I've found here, how much they're due to, say, temporal partitioning, so species that are occurring nearby, just not calling at the same time, or whether it is more to do with a spatial aspect. I guess because this data has been collected, I guess, sort of in an opportunistic fashion from citizen scientists, we don't really have a good sampling regime to easily test some of those hypotheses, but there's definitely scope to do more of that.
Right, thank you. Sorry, we don't have time for more questions, but I invite you to answer them by the chat. You will find them there. Let's move on to the next speaker. Now from Spain, Irene Alcocer, who will talk about acoustic indices. Oh.